Okay, I think it's everything is fixed. Sorry for the delay. It's our first appointment in this room for the GGI Tea Breaks, and we are very happy to be here also with the audience, in-person audience. And I just leave the microphone to Andrea, who will introduce the speaker. For being here.
Hello, everyone. So today is the first GGI Tea Breaks in person. So we have 25 people in the room. They are participating to the workshop at the GGI. We are very happy to have Savas Dimopoulos as a speaker today. I think the title is very suggestive. And I don't think Savas needs an introduction. But since there are many people in the audience, especially online, maybe a very short one. So I think it's fair to say that Savas, during his long career, has made several seminal contributions in the field of particle physics and physics beyond the Standard Model. And it's also fair to say that his works have usually influenced the experimental searches. So we are very happy to listen to him.
It's very nice to be here. This is my fourth extended physics visit to GGI, and I always have great time here. Is this okay? Okay. Okay, so it's doubly nice this time because this is also my very first talk post-COVID, in-person talk post-COVID. And I'm looking forward to the next 3 weeks when I'll be here talking physics with the many visitors and participants. So my talk will be about physics as I view it, particle physics as I view it, and the directions that we may be learning about. I will start with the traditional summary that the Standard Model has been established. It's a complete theory, almost a complete theory. It contains about 20 particles and 20 parameters, in terms of which it explains most of the phenomena that we observe in the universe. And I say most, of course, because there are still some things that it leaves out, most notably the dark matter. So it's most likely not a particle of the Standard Model, or we already know that the Standard Model is incomplete. And there are some very fundamental problems that the Standard Model does not explain. For example, it has 20 parameters and 20 particles, and that doesn't sound like a minimal theory. We would like to understand the values of most of these parameters from first principles, if possible. And in particular, among these many parameters that the Standard Model leaves unexplained, there is a few that are extremely small and beg for an explanation. And one of these parameters is the extent to which atoms are neutral. For example, the electrical neutrality of several atoms has been tested to a precision of about 10 to the minus 22. This means the electron and the proton charge are equal to each other to this precision. In fact, if this was not the case, and the electron and the proton charges were off even by 1 part in 10 to the 19, the universe would be very different. Gravity would no longer play the dominant role in the bulk behavior of the Standard Model matter. Then there is the famous gauge hierarchy problem, which is the relative strength of the weak forces and the gravitational force. And finally, the cosmological constant problem, which is the extreme smallness of the vacuum energy compared to its natural value. So these three small numbers have suggested new directions and have played a key role in the last 50 years in going beyond the standard model. And the first small number to be explained in the early days was the electrical neutrality of atoms, the so-called charge quantization that follows in non-abelian gauge theories leads to quantization of charge for the same reason that the angular momentum of elementary particles is quantized, electric charge is quantized because it obeys a similar algebra. So this gave a tremendous boost to grand unified theories, which set the stage for beyond the standard model physics in the early 70s. Another success of beyond the standard model physics is the famous gauge coupling unification, which works to a 2% precision for symmetric grand unified theories. And that has also been established since well, it was theoretically proposed in the early 80s and then experimentally confirmed in 91, leading to a great excitement about the possible discovery, upcoming discovery of supersymmetry, which, as we know, didn't materialize yet. Well, I will talk much more about it later. Excuse me, do you have a pointer? Another? Yeah. And I can use this to advance the slides, I assume, but there is, I don't know if there is a pointer, a laser pointer or something. Yeah, this doesn't work. Okay, well, I'll keep going. Do you turn it off? Oh. Okay, it's okay. I can change my slides. It's okay. Okay, so I was saying, so we have a couple of numbers that are left to explain. In the gauge hierarchy problem, we have the weakness, the weakness of gravity relative to the weak interactions, and but for the case of the cosmological constant, the vacuum energy compared to the Planck scale. And these two problems have been the focus of physics for the last 40 years, especially the gauge hierarchy problem. And there is a variety of approaches that have been incorporated to address this, the gauge hierarchy problem that I want to go over. And these two approaches come in two broad categories. One is the naturalness approach, which is trying to use symmetries or dynamics to explain the smallness of the weakness of gravity. And then there is other approaches. Let me try to give you examples of both so that you can, historical examples, so that I can remind you cases in which naturalness, for example, explained very small numbers in nature. And the first example that is the hydrogen binding energy. The hydrogen binding energy is about 5 orders of magnitude below the electron mass. And this is simply understood. I'll try to use this. And this is understood as a consequence of a number of things. One is this number of 4 pi comes from the Gaussian dilution of field lines as they expand in 3 dimensions. And together with the smallness of E is about a third, can account for these 5 orders of magnitude by using Bohr's formula or quantum mechanics. A similar thing happens in Deuteron binding. Actually, the Deuteron binding is about 2.2 MeV compared to the typical nuclear scales of 100 MeV or so. And this can be understood again as a result of a similar similar computation, except now the coupling constant is not of order a third, but it's about 1. Pi plus pi 0 mass difference, famous example where they would be degenerate. Their splitting comes from electromagnetic effects, from that the pi plus has an electric energy, whereas pi 0 does not. KK bar mixing is a very famous example, comes because of an approximate flavor symmetry in a 2-flavor model. There is a symmetry of the theory above the charm quark mass. You cannot tell the various flavors apart. And electron mass, we don't have an understanding of the magnitude of its smallness, but at least its smallness can be protected by a symmetry that is called chiral symmetry. And this is another point that I'll come back to very soon. So these are examples where symmetries either explain small numbers or at least made the smallness reasonable by a reason of symmetry or the dynamics. Then there is cases where the small numbers appear accidental. For example, the Earth-Sun distance, which is very important for our existence. It's just about right to allow the Earth to be neither too hot nor too cold for us to exist. Of course, if you believe that there is only one solar system, it's a big mystery. But if you have a lot of solar systems, like we do in our universe, it is an accident, and it's called environmental selection. Namely, we could only exist in planets with the correct distance from their star. So because there are so many stars, we live in an environment where we can. So the 7 eV line of thorium nucleus is a total accident having to do with the fact that, so the 7 eV is a mystery because 7 eV is much smaller again than the MeV scales of nuclear physics. This is simply a consequence that we've looked at thousands upon thousands of nuclear energy levels, and with such a big sample, there are bound to be some outliers. So this is just an accident of large numbers. Solar lunar eclipse is just plain luck. It is the fact that the angular size of the Earth and the Moon are the same. And I can think of no reason, either environmental or symmetry, why this had to be the case. But so there is a variety of reasons why things can be small or accidents can happen. And the question is, when it comes to the hierarchy or the cosmological constant problem, which ones of these reasons apply? Is it a symmetry or dynamics, or is it an accident, or is it environmental selection? And that will be the central focus of what I'm going to be talking about. Now, as far as the hierarchy problem is concerned, after the LHC, the first round of the LHC, we are facing the same dilemma that we were facing below the beginning of LHC. We have two classes of two directions, two roads. One is the naturalness road that can be implemented in a variety of ways, with, for example, supersymmetry being the most popular one. And another road is the road of that I call here the multiverse is the road of environmental selection. And I will talk about both of these things. And at least in my view, has happened in the last few years is that we have seen, in my opinion, a turn towards the left, towards the multiverse. And I will explain to you why I think that. As far as I want to introduce a terminology that I'll be using a lot. Whenever I talk about multiverse, the word multiverse, landscape, environmental, and anthropic selection are very closely related, and I'll always be using them interchangeably. And okay. So here is the outline of my talk. First, I'll talk about a natural approach to the hierarchy problem, and this is the standard developments that have been happening over the last 40 years in particle physics. Then I'll talk about a multiverse approach to the cosmological constant problem. I will subsequently show how the multiverse arises in string theory, or sketch how the multiverse arises in string theory, and how the existence of the multiverse is closely connected with the existence of many particles, in particular many light particles that can occur in string theory. And finally, I'll talk about a multiverse approach to the hierarchy problem. In the last two, I will spend a little time emphasizing that there are experimental tests of these ideas. And I will do so mostly because the multiverse is thought to have no experimental consequences and not to be testable. And I think this is not the case. And this is one of the central things I want to emphasize in this talk. So I start with the first topic, the hierarchy problem. The hierarchy problem, as everybody knows in this room, is a disparity between the Wick and the Planck scale. And it is doubly puzzling, first because of the smallness of the ratio of the Wick to the Planck scale, and secondly, because this separation is unstable against quantum mechanical corrections. So quantum mechanical corrections, even if you input the Wick scale and Planck scale to be different, very different in your theory, quantum corrections like loop effects will tend to lift the Wick scale, which is the same as the Higgs mass, to the highest mass scale of the cutoff, to the high mass scale of the theory, the cutoff of the theory, which I take to be the Planck scale. So we need to find some way to protect the Higgs field from getting such a big mass. And the way this was found was essentially an analogy with a historic example, which goes back to the 19th century. One puzzle of 19th century physics was to understand the electron, why the electron is so light. If you compute the amount of electric energy stored around an electron, you find that that energy diverges down, is ultraviolet divergent, has short distance divergent, which if you cut off by the Planck scale, would suggest that the energy carried in the electric field is of the order of the Planck scale itself. This is a problem that worried a lot people like Abraham and Lorentz and several others. And the problem reappears in non-relativistic quantum mechanics, where again, the self-energy of the electron is linearly divergent. However, once you introduce Lorentz symmetry, this linear divergence is tamed. And the reason why it's tamed is because when you extend the theory of the electron to incorporate relativity, you introduce new particles, the positron, and the positron adds an additional contribution to the self-energy of the electron, which is exactly negative and exactly the opposite of the linearly divergent contribution that you had before. So that the electron mass shift is only now logarithmically sensitive to the cutoff. Instead of being very linearly sensitive to short distance physics, it's only logarithmically sensitive. Now, this is not just an accident. We can understand it by symmetry. And when you introduce a positron, and you go to the relativistic theory and introduce a positron, there is a symmetry of the theory that is that surfaces when the electron mass goes to zero, and it's called chiral symmetry. And it's that enhanced symmetry that occurs when the electron mass goes to zero that is responsible for the fact that the electron mass shift has to be proportional to the electron mass itself, and therefore the remaining sensitivity is to the short distance physics is only logarithmic. So that was the motivation essentially for trying to find solutions to the hierarchy problem by using a symmetry. And the symmetry that, in fact, the QED example suggests is a supersymmetry. Now, the reason why the correction to the Higgs mass was large is because the Higgs mass is not protected by symmetry. What supersymmetry does is it relates a scalar with a fermion so that if supersymmetry were exact for each scalar, there is a fermion that is degenerate with it. And in general, for each boson, there is a fermion that's degenerate with it. And therefore, if the fermion is light, then the scalar itself can be light because it's protected by the symmetry, the chiral symmetry that protects the fermion. So, of course, supersymmetry, as I'm advocating it here, has to be extended to all the particles of the standard model. Okay, so for each particle, there is a supersymmetric particle. In particular, the Higgs has a superpartner called the Hexenos, and the lightness of the Higgs can be understood because of the existence of the Hexenos. The chiral symmetry that protects the Hexenos also protects the Higgs. Now, supersymmetry cannot be an exact symmetry. It is broken because the lepton, the electron does not have a supersymmetric partner that is at 511 keV. Nevertheless, even today, the scale of supersymmetry breaking can be relatively light. I mean, relatively to the Planck scale, can be about a TeV or so. So if the scale, so in the presence of supersymmetry at a TeV, in addition to the top quark loop contributing to the Higgs mass, the stop loop will also contribute. The supersymmetric partner of the top will contribute. It will cancel the dominant divergence and will leave you a contribution that is proportional to the supersymmetry breaking scale square. So if supersymmetry breaking is at a TeV, you can understand why the weak scale is relatively low. Now, originally, when this idea was utilized in 1981 to be used for the hierarchy problem, of course, we thought that the SUSY breaking scale was going to be around the W boson mass because that's, well, that's where the weak interaction scale is. As we know now, there were no superpartners found around the W boson, and now the scale of SUSY breaking is about, depending on the particle, is about a TeV or so. So there is still a remaining puzzle for the lightness of the Higgs why is the Higgs so much lighter than the TeV, which requires tuning the theory to about a part per thousand or so. Now, one of the great successes of the supersymmetric standard model came early, came in 1991 when LEP turned on. When LEP turned on, the gauge couplings of SU3, SU2, and U1 were measured very precisely. And if you extrapolate their values to high energies using the ordinary standard model or the supersymmetric particle content, you find that the supersymmetric one leads to unification, whereas the non-supersymmetric does not. And this was the great reason why back in 91, everybody got excited that supersymmetry was around the corner. Surely LEP is going to find the super partners, and for sure the LHC. And it was not meant to be so far. In fact, here is the extent. This is one of the most embarrassing plots I can show. It's the mass. So horizontally, you see the present limits on the gluino mass. And the vertical axis is just a light neutralino, the lightest supersymmetric particle. The important thing to notice is the gluino mass is constrained to be less than about 2.5 TeV or so. This is one of the most severely constrained particles because it carries color, so it's abundantly produced at the LHC, at the Hadron Collider. Other particles are not as well constrained, in particular particles that have electroweak quantum numbers only and no color could be around 200 GeV or so. But nevertheless, the theory is severely constrained. So now I want to move from the gauge hierarchy problem to the cosmological constant problem. Unfortunately, for the cosmological constant problem, I don't have any natural solution that I am aware of to present. So I'll move directly to the multiverse approach. The cosmological constant, there are three fundamental scales in the standard model: the Planck scale, the Wick scale, and the cosmological constant. The cosmological constant, which is like the fourth root of the vacuum energy, is vastly smaller than any other particle physics scales, yet it plays a tremendously important role in our universe because it dictates whether galaxies can form. If the vacuum energy is very large, for example, as typically it would like to be, let's say, in fact, close to the Planck scale, simply by quantum mechanical corrections. If it was much larger than what it is, it would rip apart galaxies. Galaxies couldn't form, and this means stars wouldn't form, and we wouldn't have a home to live in. So back in 1987, Weinberg used this observation to postulate the following, that first of all, let's start in a theory, in a normal theory with just few ground states. Few ground states, let's say just 2 ground states. If you have a theory with just 2 ground states, to have one of these ground states have vanishingly small energy, 10 to the minus 3 electron volts to the 4th, the present value of the cosmological constant, would be a miracle. It would look like divine intervention. And it would look like divine intervention because it's as if someone cares that we exist and adjusts the value of the cosmological constant to be small enough for galaxies to exist. Weinberg essentially inverted this argument and pointed out that in theories with many, many vacua, with sufficient numbers of vacua, then the existence of at least one vacuum whose vacuum energy is small enough to allow galaxies to occur would not be a miracle. Okay. So so our universe, the value of the cosmological constant or the vacuum energy in our universe could be anthropically selected. Therefore, if there are enough universes, we would naturally live in the one where we can live. That was 1987 when he made this argument. This was a decade before the cosmological constant was measured, and Weinberg's prediction was within about an order of magnitude of the measured value. That caused somewhat of a phase transition in people's thinking. It's fair to say that for a decade, Weinberg's paper was somewhat ignored by the mainstream. Yet the fact that it had a correct prediction changed several people's minds. An analogy, perhaps a historical analogy, helps you appreciate the magnitude helps you appreciate this the anthropic principle as applied to the whole universe. The anthropic, there was a time, once upon a time, back in 1600, most people believed that there was just one solar system. And in that solar system, the fact that the Earth is at just the right distance from the sun and has all the right properties, the right chemical elements, etc., to allow for life to exist, seemed like a miracle. Of course, today, this is no longer a miracle because we know from observation even that there is many solar systems, about 10 to the 22 solar systems. So it is no longer a miracle that there exists some planet in some solar system which has the right conditions for us to exist. Now, this observation seems obvious to us now, but back in 1600, it was somewhat more controversial. And the first person who dared to make this observation in the recent times, Giordano Bruno, was actually burnt at the stake. And in fact, this is a warning, especially to young people that are, advocating the anthropic principle, that they can get fired. Of course, people like myself don't have to worry about it, but it is definitely not a popular point of view, and I can see the reasons, many reasons why, but it may be the way it is. Many things we may not like turn out to be true. And so the analogy now is that instead of a single universe, where again the smallness of the vacuum energy would look like a divine intervention, is automatic if you have many universes we environmentally choose to live in where we can. So this is the analogy that the solar system of the 1600s is now becoming the universe of our era, and then planetary distances becomes the vacuum energy, and the universe becomes the multiverse. And now the big advantage of the previous point of view is that there was inventions, astrophysics advanced, telescope was invented, and we started started looking at the universe and finding out that there is more to it than our planetary system. So what we need is an analog of the telescope to test these ideas, and perhaps precision observations from astrophysical small-scale experiments as well as large-scale experiments can illuminate this. And I want to mention at least some possible ways in which this idea of the multiverse can get some support from observation. Now, next I will go to a big parenthesis, but an important parenthesis about how the multiverse or many different vacua or many different solutions can come about in string theory, and how such solutions can be followed by other experimental signatures. Now, in string theory, you can represent. We know that there are extra dimensions. There is 6 extra dimensions. If we represent our 3 dimensions with this plane, and the 4th, the perpendicular one, represents the space of extra dimensions, the extra dimensions we know experimentally, because we haven't seen them yet, they have to be compact. They have to be compactified somehow. And they can be compactified in an enormous number of different ways. They can be compactified to a circle, to a donut, to a 2-hole donut or a pretzel, or to a complicated, to a very complicated manifold with very many complex topology. Okay. And each one of these compactifications corresponds to a solution of string theory, or a different vacuum, if you wish, of string theory. Each such compactification has different physics, the types of particles that arise, and the types of the values of the fundamental constants depend on the compactification manifold. Okay? So each compactification corresponds to new physics, and there is countlessly large numbers of compactifications. Numbers like conservative numbers like 10 to the 500 have been enumerated. So extra dimensions of string theory contain many solutions, plenty of universes. And each one has different laws of nature. Each one has different particle content, different coupling constants. Furthermore, associated with this complexity of compactified manifolds, there is an abundance of particles. And I want to spend a couple of slides giving you some indication of how such an abundance of particles can arise, and why several of them are expected to be light. Okay. And the existence of such light particles, if confirmed by experiment, could be a signature of the multiverse. To do that, I'll give you a very simple toy example of how light particles can come about in string theory by giving you an example from ordinary, from the ordinary world that you're familiar with. Consider a solenoid, and now, as we know, the magnetic field, there is a non-trivial gauge field configuration. So when you turn the solenoid by 90 degrees, you see that there is a non-trivial topology associated with the gauge field configuration. And one interesting statement is that where all of the energy of the solenoid is carried inside the solenoid. So to create this non-trivial gauge field configuration, you have to expend energy inside, but there is no energy outside. There is no electric field or magnetic field outside. So there is no energy stored in where the topology is. All of the energy is at the center. So if you consider now a topologically non-trivial manifold where there is a hole at the center, where there is nothing at the center, then you are left with a topologically non-trivial configuration that carries no energy. And that is a cartoon of how massless particles, when this phenomena happen inside the extra dimensions, this can give rise to massless particles associated with topology. And because I should again, because there is in non-trivial, in complicated manifolds, there can be a lot of different handles and topologies associated with the 6 extra dimensions. In general, you expect many such particles to occur. Now, these particles don't necessarily stay massless. They can get masses from non-perturbative effects. However, I'll give you a very simple argument for why these masses can be light. These masses can be light provided that the non-perturbative effects that give rise to these masses are proportional to some exponential of minus some action, and this action can be thought of as some 2 pi alpha action, that 2 pi over alpha action that is, for example, associated with instant-on field configurations. In string theory, these actions are associated with the areas or the volumes of the topologically non-trivial spaces that give rise to the light particles. If these volumes in string units are large, then these particles are naturally light. Now, there is an argument, what I'm presenting in this slide is an argument for why, at least for the QCD axion, these actions have to be, the volumes associated with these manifolds have to be large. The QCD axion, in order for the QCD axion to solve the strong CP problem, the contribution to its energetics, its energetic must be dictated purely from low energy physics, from QCD physics, from physics at 100 MeV. Now, if such an axion gets a mass from any short distance physics, from any Planckian physics, then in general, you would expect that its mass could be of the order of the Planck scale, or its potential could be of the order of the Planck scale. In order for the QCD instanton to solve the strong CP problem, the corresponding non-perturbative effects that give mass to this instanton must be extremely, that give mass to the axion must be extremely suppressed. So the areas of the associated manifold must be large. So this must be the case for at least the QCD axion. If the QCD axion is not special, then this is a strong argument for large volume compactifications, which could give rise to many, many light axions. So now, in addition to the light particles that emerge in string theory can have spin 0 or spin 1. They can have, and there are other potentially light particles that can emerge that come under the name dilaton moduli radians that are associated with the shape and the size of the extra dimensions. And of course, there is also higher dimensional gravitons that can modify gravity at short distances. So there is a plethora of potentially light particles that emerge in this theory. They have many experimental consequences that have been studied for over the last 20 or so years. They can mediate new forces. They have astrophysical signatures, and they can be excellent dark matter candidates. And there is a plethora of experiments that now are looking for these things. For example, the axion, the famous ADMX experiment, which looks for axion to photon conversion in a B field. Spin precession experiments, where if the axion is the dark matter, it can interact with spins and cause them to precess. Dark photon to photon conversion experiments. And some other very interesting effects are if what makes the dark matter is a modulus that dictates the value of a fundamental constant, like the fine structure constant or the electron mass, then if this modulus is the dark matter, it is a wave that depends that has time dependence, and therefore the value of the fine structure constant or the electron mass can change with time. So this means that this can be tested, for example, by resonant mass detectors. If the fine structure constant changes with time, the size of an atom changes with time, it breathes. And as an atom breathes, a solid breathes. And that looks like a wave that can be detected by resonant mass detectors. And there are experimental proposals to do that. And similarly, if you have two atomic clocks whose whose energy levels depend differently on alpha, if alpha has time variation, then the two clocks that start out synchronized will get out of sync, and you can do this. You can look for this with very high precision. So and one of my most favorite effects that don't even depend on having the axion be a dark matter is the black hole superradiance. So a rapidly rotating black hole can simply create a cloud just from quantum fluctuations. It can just create a cloud of axions, which can lead to observable signatures like gravitational waves, for example, emitted by this axion cloud. So there is a huge amount of activity around these particles. And I feel that these are some of the most well-motivated particles to look for, both as a dark matter and as potential candidate, even if they are not the dark matter, things to look for because they can change force law, they can mediate new forces, or they can be produced by superradiance, etc. And now I come to a topic that is a bit less studied, multiverse approach to the hierarchy problem, or split, and in particular split supersymmetry. Okay, I will start with the following question. Whether a crucial element in Weinberg's argument about the cosmological constant was the statement that the vacuum energy is crucial for galaxies to form, and therefore it cannot be that large. An important question that Agarwal, Barr, Donohue, and Shekel asked back in '97 is, whether one can apply a similar argument to the weak scale, not the vacuum energy, but the weak interaction scale. And they had their very clever idea was the following, that the value of the weak scale, of course, determines the quark masses. And a neutron has 2 down quarks and 1 up quark. A proton has two up and 1 down. And the Yukawa couplings of the up and the down quarks are different. So as you crank up the weak, the vacuum expectation value of the Higgs, the down quark becomes much heavier than the up quark. And conversely, if you drop the vacuum expectation value of the Higgs field, the up and the down quark masses, well, they both will go to 0. So now, what does this imply? Imagine that you start with our world where the weak scale, the W mass, says 80 GeV. As you start decreasing, if you start decreasing the weak scale, for example, that would be the case if you believe that the weak vacuum expectation value is 0 because there is some, humongous positive mass square for the Higgs. Then as you drop the weak scale, what happens is the proton mass, the neutron mass becomes smaller and smaller. It approaches the proton mass and it eventually becomes lighter than the proton. So all the protons will decay into neutrons. So there won't be hydrogen atom. And conversely, and without hydrogen, of course, you can argue that at least life would be nothing like what we observe it today if it would be possible at all. Chemistry would change, biology would change in a way we cannot even track. Similarly, as you start cranking up the weak interaction scale, the neutron becomes much heavier than the proton. The neutrons inside an atomic nucleus now can start decaying into protons because the neutron-proton mass difference is much bigger than the QCD scale. And eventually you lose all heavy nuclei. You have only hydrogen for a while. Again, a very unfamiliar environment for life. And if you keep, in fact, increasing the vacuum expectation value more, the neutron, the down quark mass was becomes so heavy that the lightest baryon is a bound state of 3 up quarks. So then you would have, this looks like a helium nucleus, and you would have essentially some heavy helium type universe, something again that, so they argued that the weak scale, you cannot change the weak scale by more than maybe factors of 2 or 3 before you run into trouble with chemistry. So we'll adopt, we call this the atomic principle because it sounds like the anthropic principle, because that's how we want to use it, is that the presence of atoms, all atoms that you observe, is we impose as a criterion for the existence of life. And so this criterion could be used to fix the weak scale around where it is today. And armed with this anthropic specification of the weak scale, you can propose the theory of split supersymmetry, which goes as follows. At very high scale, you start with, you have scalar superpartners, let's say at scale above 10 TeV. Then as you go down in energy, around the TeV scalar, so you have fermion superparticles, fermionic superparticles. Notice that fermionic particles can be protected by chiral symmetries. So they can be around a TeV or 10 TeV with, just on grounds of chiral symmetry. The scalar superparticles are at the scale where supersymmetry is broken, which we take in the theory of split supersymmetry. We take the scale where supersymmetry is broken to be high, at least 10 TeV or higher. Now, it turns out this is a good choice for practical phenomenological reasons, flavor changing neutral currents, and all kinds of electric dipole moments, all kinds of phenomenological constraints on supersymmetry are automatically satisfied once you make the scalar superpartners heavy. And of course, you have the Higgs fixed by the atomic principle that I just advocated is like the successful prediction of gauge coupling unification that is in supersymmetry is preserved in split supersymmetry. And the reason for that is that the most important thing for gauge coupling unification are the fermionic superpartners and not the scalar. The scalar superpartners are complete SU5 multiplets, so they don't really contribute to the relative running the coupling constants. So because we are keeping the supersymmetric fermionic superpartners light, the successful gauge coupling unification is preserved and works at least as well as ordinary supersymmetry. And this one is a very dense transparency. I'll just summarize it by saying that here is a plot of the fermionic superpartner masses and the scalar superpartner masses. To fit the correct value of the Higgs mass for various values of tangent beta, you are constrained to these Brazilian colors. And gauge coupling unification suggests that you should be in this on the left side of this plot, which implies that the particles, that the Hexenos, the fermionic superpartners, must be around 100 TeV or lower, 10 TeV or lower, just to get the correct the gauge coupling unification and Higgs mass. There are several pretty spectacular signatures for split supersymmetry. For example, for the case of the gluino, because the quarks are heavy, the gluino becomes automatically long-lived, and its lifetime can be it's long enough that it can live. It can have a displaced vertex of about 10 to minus 2 meters. And that is a unique signature, 2 jets plus missing energy with a displaced vertex. Similarly, the physics of the Hexenos of the electroweakinos in general is pretty simple because scalar superpartners are heavy. You are left essentially with the various Hexenos and winos split by electromagnetic effects. So the mass splittings of the Hexenos and the winos are calculable numbers that are given in terms of the fine structure constant, such one loop diagrams, and the Z mass, which enters. And they have very small values, about 200 to 300 MeV. And because they are so small, again, they can give you displaced vertex. They have long lifetimes to leave you displaced vertex signals. And 3 TeV winos and 1 TeV Hexenos turn out to be good dark matter candidates. Another very neat effect is that the Yukawa couplings of the Higgs to the Hexenos and Winos, as well as the quartic Higgs couplings, are all related by supersymmetry. Okay, so if you measure the Yukawa couplings of the Hexeno-Wino sector, and of course the quartic Higgs coupling at low energies, and you extrapolate them at high energies, you will find when they meet, by meet I mean when they obey supersymmetric relations, that is where the scale of supersymmetry breaking is. So when you measure this with high precision and you run them, you'll find that they meet at a specific location. This will look like a miracle because different gauge couplings, different couplings of the theory all become one. The scale where they meet is the scale of SUSY breaking. Furthermore, the scale of SUSY breaking can also independently be determined by the gluino lifetime, because the scale of SUSY breaking is the mass of this squark. So you can check this theory both by the unification of the various couplings and the gluino lifetime. So there are several non-trivial coincidences that this theory would predict, and here is what I summarize here. Now, an important question is, what could be convincing evidence for the multiverse? Okay, so as I said, that's an important question because the multiverse is thought not to have experimental consequences. First of all, we already have two pieces of evidence for the first one being vastly most important, already the smallness of the vacuum energy and the absence so far of competing explanations, let's say non-anthropic explanations or for the smallness of the cosmological constant is already an indication that this could be the right direction. The fact that we haven't seen anything at the electroweak scale may be an indication. As I mentioned, let's say we discover 100 light axioms, then I think there won't be any debate. If we were to discover 100 light particles, people would agree, okay, there's probably complexity string theory will become. What about 10 light axioms? Well, most people probably would be convinced that it's probably something unique. And then below 10, the threshold depends on the person. For me, if we see 2 light axioms, it will be already in conjunction with the first 2 observations. It would already be some significant additional evidence that we are dealing with a multiverse, with a complex structure, with a complexity that gives rise to many solutions and many light particles. Perhaps 3 would be better for convincing the rest of the particle physicists. But so looking for such light particles is exceedingly well motivated from this perspective. And finally, split supersymmetry at a high energy collider. I think probably to test the split will definitely need a high energy collider. Now, so that's what it would take probably to start convincing a fraction of the community that this direction, the multiverse direction, is the way to go, or the way nature has chosen. Question is, when will this happen? Okay, when will this happen? What is the time scale? Well, there is an optimistic scenario, three of whose elements are not that optimistic. For example, if an anomaly gets confirmed, one of the anomalies that one or several of the anomalies that have been advertised if they start getting confirmed, that could be at least a step towards beyond the standard model physics. If any one of the small-scale experiments or astrophysical observations that are being discussed in the last couple of weeks in this workshop make a discovery, that would be a boost to BSM physics. Perhaps a high luminosity LHC could make a discovery that would this direction, even though it doesn't have the advantage of having, higher energy. Perhaps with high precision, we could learn something. And then there is the more optimistic scenario, probably too optimistic, that require a few glasses of wine to believe in, is, for example, imagine convincing Jeff Bezos that super colliders are cool, or Elon Musk may be a better candidate for that. And so that could really accelerate things. I mean, if such a person wanted, probably they could, within a decade or 15 years, we could have a 100 TeV, choose your collider, let's say Hadron Collider. That's a bit unlikely, but it's something that we should aim for if by talking to such people and having them appreciate what it is we are doing. And one, I think, maybe easier possibility is, let's say that there is some significant progress in magnet technology that leads CERN to prioritize a 30 TeV collider in the present tunnel. Okay. If CERN decided to do that, I think within 10 or 15 years, we could probably be exploring definitely a new frontier in energy. So these the conclusion I want to draw from this is that far from thinking that the multiverse is a theory with no predictions, I think it opens many opportunities for discoveries in all kinds of experiments. And in fact, it underlies the preponderance of light states that can emerge from string theory, makes it even more important to have, even beyond collider, many small-scale experiments, as well as, of course, astrophysical observations that look for such particles. Thank you.
Thank you. So time for questions, both from Zoom and from the room. So there is Misha.
Yes, thank you. Thank you. Thank you, Savas. I would like still to emphasize that even if you see 2, 3, 5 very light axion or axion-like particles, I don't think it's a very serious argument in favor of multiverses, because there are many reasons why, and many other symmetries which are slightly broken, let's say in the dark matter sector or whatever, which produce gallstones, and these gallstones then acquire a small mass. And even if you say insist that it's a hint of the multiverse, it's a very, very indirect hint. And in the direct sense of this world, the multiverses are directly unobservable, because there is no causal signal which can be emitted in one part of in one universe and reach another universe. And this is the only direct, this would be the only direct observation. And the second thing in this comment, that even if you accept, you say, let's say this multiverse scenario paradigm, it's like a religion. You can strongly believe in it, even in the absence of direct observation. It's a philosophical issue. But if you do believe, you don't need axioms at all. Because in one of the universes from multiverse, the theta parameter will be small accidentally. That's it.
Okay, time for a replay.
No, I'm having. Do you guys understand? I cannot. I can tell that I cannot understand the question.
It was very clear, at least on Zoom.
Yeah, I am sorry that the sound is extremely bad. I get that you're not convinced by seeing a few particles that it would be it would be evidence for the multiverse, and that's a fair argument. But I couldn't understand any of the details. So if anybody heard more clearly, oh, Nima seems to have heard more clearly, then I would appreciate.
Can I just make one comment? I'm not gonna, I'm not gonna speak for Savas, but I just want to make one comment, Misha, that in principle, I mean, that there is an aspect of the multiverse which is in our heads, perhaps, which is whether all these sort of vacua are out there and are populated beyond our cosmological horizon. But there's an aspect of it which is in principle completely verifiable in low energy experiments, in principle. If you imagine, just imagine that you did have n light scalars, and just to take a very simple model, imagine that each one of the n light scalars had a generic quartic potential. They're just real scalars, so with a cubic and quartic coupling. So that means that each scalar has a potential with 2 vacua, which are not degenerate. And if you have n of them, there's 2 to the n vacua right there. You can confirm in principle in experiments in our universe that you have n light scalars, and you can even confirm that they have the shape of a potential that would allow them to have an exponentially large number of vacua. The fact that you could have exponentially many metastable vacua is something that's in principle observable in one universe. What may not be observable is this sort of picture that they're realized out there somewhere beyond our horizon, eternal inflation, blah, blah, blah. And there may well be some element of that picture that's wrong or misinterpreted or something. But I think if you see n light scalars and you see that they have sort of, it's in principle possible to see that they have exponentially many vacua, that would certainly change. I think it would be objective evidence that that we have to take into account the possibility of an enormous number of metastable vacua in our thinking about tuning issues.
Okay, I agree. It may in principle happen. We have to wait to see whether it happens. But what I want to emphasize, you will still would not know for certain that these many light particles are due to multiverse, right? They may occur for different reasons.
I'm saying something else. I'm saying these many light particles could give you all by themselves a multiverse. I mean, a landscape just by themselves, independent of where they came from. That seeing that you have, like, 100 scalars with each 2 minima tells you there's 2 to the 100 vacua, whether you like it or not.
Well, okay.
Okay, I think that John raises his hand, so.
Yes, hi, Savas, can you hear me?
Hello, yes.
Hi, nice to see you, even if only in 2D. My question is the following. You seem to have an equation which is multiverse equal to anthropics, or environmental selection. And I think that the multiverse is a lot more than anthropic. Anthropics is one mechanism for selection. but I think there could be many others.
Yeah.
And so the multiverse is a lot richer than just anthropics.
Right.
And it's also dangerous to convey the message that multiverse is just associating necessarily to anthropics, given that some people have such a strong religious reaction against it.
Yeah, no, I agree with you. Actually, I said how I would use the terminology, and it's widely used. But if it's true that in principle one can envisage some dynamics within the multiverse that can lead to some preferred places in the multiverse that are preferred for dynamical reasons, not anthropic.
We have a question from the chat. I think. Okay. And Stuart. So please, Stuart,
Yes.
you can unmute yourself.
Yes, so hi, Savas, it's good to
Hi,
see you
Stuart.
again. It's been a long time.
Yes.
I look at your figure, which is multiverse on one side and naturalness on the other side. It seems to me that split supersymmetry or mini split supersymmetry naturally connects to the other side of the diagram. And so there should be a circle there connecting naturalness. In other words, mini split supersymmetry is on the edge of naturalness. And it seems to me that that diagram should show that.
Okay, that's a good point. I'll think about it for my next talk.
Any question from the room? Yeah. The chat. But the chat is a question for Nima.
So you say that complicated string compactification, they give you automatically a lot of light particles. But this forgets completely fluxes, which is what people invoke for stabilization. So does this belief survive, really realistic compactifications?
Absolutely, yeah. Yes.
In the moment that you put fluxes into
Yes.
this complicated,
Right. Some things will get
these
massive.
actions will get mass at 3 level and will be huge. So,
Absolutely, yes. But
so
this doesn't
why are
include
so
that
confident that this
no,
string theory
we are not
compactification will give you a lot of
confident.
actions?
There is potentially many topological objects that can be topologically light, and turning on fluxes will give masses to some, but not necessarily to all of the ones. Yeah. It could be unlucky and have, or lucky and have only the QCD axiom. But there is in principle such a complex topology associated with these enormous manifolds. And given that the QCD axiom motivates large volume compactifications, that there will be other axioms that will be light too. But it's by no means guaranteed the existence of these light particles. But I think, especially if you want to have the QCD axiom and keep it light, keep its dynamics controlled by QCD and not by Planckian physics, then I don't think if we have the QCD axiom and it hasn't been polluted by stringy effects, then I think that's a strong indication. That's an indication that we can get lucky and have other light axioms too.
Do we have an estimation of the number of light scalars that we are expected to have in our universe?
I didn't understand the beginning of the question.
How many light scalars do we expect in our universe, for instance, based on string theory? How many light actions?
No, we don't have any idea. Yeah.
We don't have an estimation in string theory?
there could be hundreds of these cycles. There could be zero if they are all. If it could be that only one escapes and is light, like the PCD axion, or maybe there is no PCD axion, and then it could be because they are all heavy. Or
Okay, thanks.
So there is an ongoing discussion in the chat. Yeah. So the first question from Glenis Farrar was about, is it really possible to have direct evidence of these 2 to the n vacua in the example given by Nima?
In the example given
by Nima, so Nima was discussing a possibility to build a, okay, maybe he can speak up for himself, but a model with 2 to the n vacua, and the question is, can you really have a direct evidence for this?
I can say what I had in mind. It was, I thought he was saying that you could actually do experiments that would let you probe those other vacua. That would be, of course, spectacular. But from his answer in the chat, it seems like maybe he's just saying that they could each have different parameters, and you would see that they had particles associated with them and stuff like that. But that seems different from saying you could actually somehow do tunneling experiments into other vacua.
You wouldn't even have to do tunneling. In principle, if we had all these light scalars, I mean, I'm making a trivial comment. If you have n light scalars with these 2 non-degenerate minima, the domain wall tensions between them can be big. There's no problem. Just, I mean, this is the basic mechanism also where flux vacua come from. This is why we can get exponentially many vacua. It's just a sort of stupid mechanism that if you have n things, you can get exponential in n vacua in this trivial way. But imagine that you had this, you could actually make bubbles of the other vacua. You could make, in principle, you could make regions where the scalars move around, and experiments could make bubbles of the other vacua. What you cannot do, and this is the part which starts getting interesting, what you can't do, we can't know whether they're really realized out there somewhere beyond our horizon. We can't check that, of course, with experiments. You also can't make vacua sort of big enough so that they become their own universes inside cosmologically. In other words, you can't make these sort of shells of the other bubbles big enough so that there's a sort of Hubble regions, internal Hubble's regions worth of size, a vacuum in there, without that region collapsing into a black hole. I mean, this is all related to the Guth-Farhi problem of trying to produce universes in black holes and so on. However, you certainly could make bubbles. In principle, experiments in one universe could make bubbles of the other vacuum. You could shoot particles into there and see indeed that the couplings of the scalar changes the couplings of the standard model. You could verify all of that. So there's an aspect of the multiverse that has nothing to do with the speculation of philosophy and bullshit and what's going on beyond the horizon, which is just related to whether you see n light states. Light here could be at the gut scale. They just have to be sub-Planckian in order for you to be able to confirm that these vacua are there. N light states with some difference so that you get a large number of vacua that are not identical.
Okay, I have a completely unrelated question. So Misha Shaposhnikov most claimed that the hierarchy problem is nothing else than a mirage of the way how we actually calculate observables in renormalized QFT, and he offers a different operational procedure to do that. I don't know if you're aware of the paper, but if you are, do you have a comment on it? By Shaposhnikov yesterday or 2 days ago. You don't know, okay. Then.
Other questions or comments? Well, if not, let's thank Savas again.